Okay, so good evening. My name is Mansi Tripathi. I am TA for this particular course, Environmental Chemistry. So welcome to week 4 of the problem solving session. So what I will do, I will first start with some introduction. I will start from the basics of this acidity and basicity, means acid-base reactions. Then we'll solve the problems for the assignment for this week 4. So that will be sample problems, not exactly what have been given in the assignment. Okay, so I'll start with some basics, then we'll go through them. Okay, I'll share my screen. Allow me a moment. I hope this is visible. Okay, so I'll start now. Okay, so we'll start with acidity and alkalinity. So first, what is alkalinity and what is acidity? So alkalinity is basically, when we say alkalinity, I will represent ALK for alkalinity. So it is acid neutralizing capacity of water. We are talking about water here. It is environmental chemistry. So basically we'll be talking about water, concept of water. So alkalinity is the acid neutralizing capacity of water. It can neutralize acidity of anything, but here we are mostly talking about water. Secondly, so presence of strong base and weak acid or a salt of weak acid. Okay, so this makes up alkalinity. So what does makes alkalinity? First, there can be strong acid or strong base, or there can be weak acid, presence of weak acid plus salt of a weak acid. So either strong base or weak acid or salt of weak acid makes up alkalinity. So for example, if we say, could you please mute yourself? Thank you. So if we say that NaOH is there, which is a strong base, and if we are reacting it with NH2CO3, which is a weak acid, so whatever it forms, this NaOH is going to neutralize this acid. So is this whole process refers to more alkalinity of NaOH rather than, so this whole solution, whatever will we get, even if both are present, acid and base, but whatever we'll get, it will be more of alkaline solution. Okay, so another thing is acidity. So it is, what is acidity? It is base neutralizing capacity of water. Okay, so it is a solution of strong acid, and it is a solution of strong acid and weak acid, or salt of weak acid. Okay, so that is why, because how salt of weak acid is going to it becomes, like how the strong acid will react with something salt of weak acid, because if there is a salt of weak acid and it gives out the H plus, for example, if we take, okay, if we have this as acid, okay, and something is reacting and strong acid is reacting with it. Okay, and after being in solution, if it is in solution, what will happen? H plus will go away. So we will get CH3 C double O. If it is reacting with sodium hydroxide, then it will be CH3 C double O Na. So for I'm just writing it like this. So what will this become? This will become a conjugate base. Okay. So these are different kinds. This is the definition of alkalinity and acidity. So this is just basic definition based on water. There are many different definitions as well. So for now, we'll stick to water. Now comes what are different types of alkalinity. So there can be caustic alkalinity, or there can be phenolphthalein alkalinity or methyl orange alkalinity. So these are the different definitions of alkalinity. For example, so what is caustic alkalinity? So caustic alkalinity is the presence of some strong base. So where there is presence of some strong base, so whereas there is presence of strong base like NaOH or something, so whatever gives OH ion, we call that as caustic alkalinity. Okay, so by definition, when we say caustic alkalinity or phenolphthalein alkalinity or methyl orange alkalinity, caustic alkalinity means it is defined as the acid required to bring down the pH to the equivalence point of carbonate system. Okay, so caustic alkalinity is the amount of acid required, amount of strong acid required. Okay, here we are talking about strong acid because weak acid will never be able to do that. So strong acid required to bring down the pH. So we want to reduce the pH to equivalence point of carbonate system. Okay, so this is caustic alkalinity. Okay, further comes, so here what is the equivalence point? Here comes the question, what is equivalence point? So for simply, how do we find out equivalence point? Equivalence point is also some pH. So some pH is equivalence point. So how do we get to that pH? For example, just take a solution of something, maybe some acid, and add salt. Keep on adding salt. Okay, and the pH at which this system reaches equilibrium, that pH is called equivalence point. So I'm just giving some basic definitions. Sir will clear this all in the future classes. So just for sake of keeping those things in mind. So when there is a solution of acid and we kept on adding salt, and at the point, it can be, the solution can be acid or base anything, and salt can be acidic or basic anything. So the point at which the system reaches equilibrium, that particular pH, if we put a pH probe here, and the pH if we are measuring, that will be equivalence point. So the amount of acidity, amount of caustic or strong base required to bring down the pH to equivalence point of the carbonate system. And why we are talking about carbonate system? Because we are talking about water. So the basic things that give acidity or basicity to water is the carbonate system, means carbonic acid system. So that is why we are talking about carbonic system in the present case. Next comes the phenolphthalein alkalinity. So there are basically two indicators available in lab. One is phenolphthalein, another is methyl orange. So phenolphthalein alkalinity. So we put phenolphthalein indicator in the solution and we find out the change in pH, find out the change in color to determine the alkalinity. So it is the acid needed to bring the pH to bicarbonate equivalence point. So for carbonate system, there will be different components like by carbonic acid, bicarbonate, carbonate ion. Like this, there will be different component. So phenolphthalein alkalinity is the acid needed to bring the pH to bicarbonate equivalence point. pH is coming to bicarbonate equivalence point. That is called phenolphthalein alkalinity. And second is methyl orange alkalinity. It is the acid needed to bring down the pH to H2CO3. Okay, carbonic acid equivalence point. Okay, so that is methyl orange alkalinity. So you don't have to remember it. Just for the sake of knowledge, I will share all these notes. So these are the equivalence point. So other important thing that we should discuss is the titration curve. Okay. Okay, so let's say this is a burette. We are using this to titrate a solution of Na2CO3. We are using this to titrate a solution of Na2CO3, and in burette we are filling it with 0.1 normal HCl. Okay, so while we keep on adding HCl, what will happen? The pH will reduce because this one is acidic and this is base here. So the pH will be, if let's say pH is around 11, it will reduce by adding acid. So what will happen? It will follow the trajectory something like this. pH is there, and let's say amount of acid added or volume of acid added, or formally it can be said H plus equivalence. So for now I will write amount of acid added. So let's say pH started from 11, so it will reduce. It will follow a certain curve of reduction. Okay, so and there will be it will be something like this. Okay, so there will be some plateaus and there will be some jump also. There will be jump and then there will be plateau. So this kind of curve will be there. But what if we are diluting, we are just titrating distilled water in place of Na2CO3, we are putting distilled water, what will happen? The curve will simply be like this, very straight. Okay, so this is for distilled water, and this is for when there is some base in the compound, base in the solution. So there will be some jump and there will be some plateau. So what is happening, actually what is happening here? So okay, so there will be various points over it. Like let's say this was point A and we added some OH ion, means caustic alkalinity, to bring down the pH till here. So this is equivalence point. After that we are changing the system. So Na2CO3 is also carbonic acid system. Okay, with some salt. So that is why we are saying looking at this basic salt. So equivalence point is this pH. Actually, this will be pH 11.2. So this is equivalence point, this acid system. So the thermodynamic, like we have studied about these equilibrium constant pKa1 and pKa2. So pKa1 for this system is 6.3 and pKa2 for this system is 10.3. So depending upon this, there will be reduction in pH, and at those equivalence point, because at these points there will be some buffering capacity, so we will see some plateau. Okay, so so all these points, like as I explained initially, there will be a rapid fall. So this is the point where it will reach pKa1 value. I will mark these points so that will be easier for you. So this is 10.3. Okay, so from 11.2 to 10.3 it will fall rapidly because there is no buffering capacity here. But at this point what will happen? Now the concentration of carbonate ion is equal to the concentration of bicarbonate ion. So at this position, this pKa2, that is 10.3, is equal to pH of the solution. So now at this position, since it has reached equilibrium and the buffering capacity, after this for some time there won't be any significant change in pH. And still if we keep on adding, there again be a rapid fall again. And this pH will be 6.3. And here again, now what is happening? Uh, so there will be again a flat point. So now carbonate system moved to bicarbonate. Now bicarbonate will move to carbonic acid. So at this point, this is going to happen. Bicarbonate will be equal to carbonic acid. So here also we will reach a plateau. So basically what will happen? At this point, only carbonate ion was there. CO3 2 negative. CO3 2 negative. There was no buffering capacity. We added acid. It came to 10.3. Now carbonate and HCO3 negative both are there because we are adding acid, right? So we are giving H plus. So H plus is reacting with Na2CO3. So it is forming HCO3 negative. After that, there will be buffering capacity. So there is a plateau. We still kept on adding more HCl. Now again, there is a big fall up to 6.3. Up to pH 6.3, there will be a big fall. Now there is no carbonate. Carbonate is not there, but carbonic acid and carbonic acid and bicarbonate both are there. So again there will be a plateau. So this is the titration curve. But however, for distilled water, since there is no base to act as buffer, simply we keep on adding HCl, the pH will keep on losing in a straight line. So there won't be any change. Okay. So other important concept is, so in any system, acid and alkalinity is caused by H2CO3, carbonate, bicarbonate, H plus or OH minus. So whatever we discuss, like even if we talk about acidity or alkalinity, all these things are responsible. So carbonic acid can be base in one system and it can be acid in another. Okay, so acidity or alkalinity is caused by all three. Okay, so depending upon the pH condition, the species may vary. If the pH is low, less than 6.3, this will be there. If the pH is greater than 10.3, this will be there. So all these things will be there all the time, but depending upon the pH, is it not visible? Uh,
It's visible then.
it is visible. Maybe there is some problem with your internet. I guess this is visible. Okay, you check your internet connection. Okay. So depending upon the pH, these things may increase or decrease, but they will be there. Okay. So now sir has already derived expressions for alkalinity and acidity. So I will not go into detail. I will write an expression for alkalinity. Alkalinity is equal to 2 CO3 2 negative plus HCO3 negative plus OH. This is caustic alkalinity minus H plus. So normally when we are not talking about water system, these things won't matter. But when we are talking about water system, it will split into H plus and OH minus. So that is why other things are also coming into picture. So this was the expression for acidity, alkalinity. And when we say acidity, acidity is 2H2CO3 plus HCO3 plus H plus minus OH. Okay, so in both the equation, either we talk about alkalinity or acidity, two things are common. Okay, the only change is this value and this value. So that is how acidity and alkalinity works. So what is total? C total, concentration of anything in total is equal to, if we add both the equations, we know what is this equal to. So H2CO3, this is sum total of all the species. HCO3 negative plus CO3 2 negative. So if we add both the things, what we will get? Ct is equal to alkalinity plus acidity divided by 2. So this is how what we you want to say something? Uh, your hand is red. Yeah.
Yeah, yes, yes. Yeah, so I didn't found black, but yes, work now it's working.
Now it's working. Okay, that's good. Okay, thank you. So this is for revision that sir has explained nicely whatever all these things are. I am just writing it for your revision. Okay. Now coming to the ionization fraction, which was taught this week. So there are some uh, ionization fraction terms. So we'll start from alpha naught. So this is important for you to remember these equations. That will make task very easy. Alkalinity, acidity, Ct. And this you can also remember, Ct is equal to alkalinity plus acidity divided by 2. Now coming to ionization fraction. So first one is alpha naught. So what is alpha naught? It is simple. H2CO3 divided by Ct. Ct we know. Ct is sum total of all the species. Next ionization fraction is alpha 1 HCO3 divided by Ct. And what is alpha 2? CO3 2 minus divided by Ct. Okay, so these are the expression for um alpha 1 ionization fraction. So basically, Sir has taught many ionization fraction of diprotic acid, triprotic acid, or you can go for Q4 acid also. But for water concept of water, these only these three are important. You don't have to go into deep. So just for writing, like uh, if we write this equation, H2CO3 is changing to H plus and CO uh, HCO negative. Okay, if we are writing this, so we will get some K1, right, which will be equal to H plus HCO3 minus divided by H2CO3, right? We will get some all these values. So from here, what we have to do is we just wanted to extract from all three equations. Like one equation will be this, and the other we know that HCO3 will dissociate into H plus and CO3 minus. So from all this equation, we want to extract the species. So that is our target. So HCO3 will be what? K1 into H2CO3. Now there is we are putting star here. So what is the star? In here also there will be star. Here also there will be some star. See, if we have a what? If we have a what solution, we are putting H2CO3 in here. Okay. So here there is no star for now. What will happen? It will start dissociating into H plus and other compounds. But still there will be some component which will be H2CO3 only. So to represent that fraction which is there as H2CO3, we are putting star. There is nothing else. So there will be difference between the initial H2CO3 added and after some time what H2CO3 fraction remains. So just to represent that, we are putting it as star. So this will be H plus. Similarly, for CO3, K2, here it is K1. So for CO3 equation, it will become K2. We are considering it as K2. So this will be HCO3 negative divided by H plus. Now, if we replace HCO3 from here to here, what we will get? We will get K1, K2, everything we will get in terms of H2CO3. Because see, why we are converting everything to H2CO3? Like if you want to know the pH of the solution or anything, you have a solution. You know some initial thing what you have added, some initial thing you have added, and you have the pH meter to measure the pH. So only two things you can know for the time being. Either the initial H2CO3 that you have added and the pH. So we do not know all these values, right? So to get that value, we are doing all this procedure. So putting all these values in CT table, H2CO3 star, which was already there, plus K1 H2CO3 star. I hope you understood the concept of star. because CT is what we have already added, but we have added H2CO3, but we cannot use that term because some of them are dissociated. So that's why for the undissociated terms, we are using star. So this might get confusing, but remember few points. H2CO star, H plus square. Okay. If we take out H2CO3, we will get 1 plus K1 upon H plus K1 K2 upon H plus. This will be square. Okay, and simply from here we can calculate H2CO3 star, because we want to know the undissociated H2CO3. CT, we know what we have initially added. If it is, we have added 1 molar H2CO3, no? So CT will be 1 molar. Okay, whatever happens, even if H2CO3 is being converted to carbonate system or anything, this CT will be, if we have added 1 molar, so it will be 1 molar. So we know this, and other thing, we know pH, and we want to calculate H2CO3 star. So very simple. Now we know CT also, we know, and this K1 K2 we already know, 10.3 and 6.3 for the carbonic acid system. So we have all the information here. This is K1 K2. Pardon for my bad handwriting. So we know CT, we know H plus, we know K1 K2. So it's simple, it's very simple to find out H2CO3, and simply we can find out HCO3 from this equation. Once we know H2CO3, we can find HCO3, and we can also find K2CO3. All these things, it will be very easier to find out. And if we write it in terms of alpha, then for this equation, if we want to write it in terms of alpha, that is ionization fraction, just to make the task easier, because so that we don't have to write big words. So that is why I mostly use this ionization fraction concept. 1 upon, because how we will get alpha? Just dividing all this equation by CT. What was alpha naught? H2CO3 divided by CT, right? So just taking CT from the right side to the left, we will get alpha. So alpha naught is 1 plus K1 upon H plus K1 K2 upon H plus square. What will be the alpha 1? Alpha 1 is equal to 1 upon H plus K1 plus 1 plus K2 H plus. Similarly, alpha 2 1 upon. So basically alpha 1 and alpha 2, what is the difference? The denominator is multiplied by H by K1. Okay, denominator is just been multiplied by, if we are taking the denominator and multiplying it by inverse of this, we will get alpha 1. So this is for easier for you to remember. Just remember alpha naught, and alpha 1 you can just, the middle term you just reciprocate it, make it reciprocal and multiply to the denominator. And for B alpha naught, What will be the value? Same. Just multiply the denominator by this term, by in reverse of this term. Okay, means just multiply it by h plus by k1 and you will get alpha 2. So what will be the value here? Sorry. So from alpha naught to alpha 1, alpha naught we want to convert to alpha 1, then we want to convert to alpha 2. Alpha naught you have to remember, alpha naught just the denominator, multiply it by reverse of, just a second, I'll add this person. Hmm. For alpha naught, alpha 1 what you have to do? Just multiply the denominator by the reverse of h plus by k1. And for converting it to alpha 2, just multiply the denominator by the reverse of h plus by k2. Okay, so this conversion you have to do and you will get the answer. So that is alpha 1, our alpha 1, alpha 2 and all these things. Okay, so now what shall we study? If we can write this whole CT equation also in terms of alkalinity and alpha 1, alpha 2 simply. So CT, this is all this revision. Sir has taught all these things. Alpha naught. For now, I understand that these concepts will be quite boring, but when we will reach to the equilibria graphs and all, no, then it will become really interesting. We will be able to know at what pH which metal will precipitate and what can be the solution for a particular problem. Problem in the sense the nature-based problem. Like if you have something like you have a solution with chromium in it and you want to reduce it, what you can do, all those things. When we will get the equilibria problems, then it will be easier to find out. For now it's mostly memory thing. You can derive it anytime, but that will be time taking, right? So you have to memorize a few things, know the basic concept, but memorize. Even I am also copying it from somewhere and writing. I have prepared notes. So this will be the CT equation. So knowing this equation in alpha naught, you will be able to solve, you will be able to find alkalinity also or pH of the solution also. So this is the, we can say, master equation for solving many problems. Okay. So why we need to study all these equations? So first I told if you want to separate out the metal from example chromium or anything. So any kind of metal precipitation, because you know the metal will be, any of these sort of substance will be least soluble at a particular pH. So it will be least soluble at a particular pH, like let's say chromium. So this is the solubility and this is pH. So at a particular pH, it will be least soluble. So you want the pH to be increased or decreased to that particular pH so that you can precipitate out the metal. Okay. Apart from that, since the water has a particular buffer capacity, right? So optimal pH dosage will be required so that we can calculate a big, like how much pH, if the water is having some buffer capacity. For example, we are getting some lake water, it has some buffer capacity, we want to increase or decrease the pH. So from using these equations only, we can get how much dose is required to reduce the pH to a particular value. Instead of doing all the trial and error, we can also do this. Okay. So important thing is buffering. So buffering is a, in a natural water system, is an important concept. Okay. So there will be only slight change of pH in that particular region. So that is, we prepare buffers also in our labs and anything. So we use all these Henderson-Hasselbalch equation and these equations to find out the correct value, how much acid or base we need to add. Okay, and we have already studied about Henderson-Hasselbalch equation. I will write this equation again. So this is for to calculate the buffering capacity. pH is equal to pKa plus log H plus acceptor divided by H plus donor. So this if we write in this form, this will be the most basic H plus acceptor minus H plus donor. Okay. Could you please mute yourself? Okay. So basically, this was the revision till now, whatever sir has taught. After that, the other equations we'll study in the next class. So for now I will show the questions. Okay, basically what we do, I'll show the questions because that is mandatory for the present course. So all you need to solve the questions and explain the concept in between. So this is the week 4 of the problem solving session. So what sir has taught is mostly ionization fraction. Apart from that, we also studied about the visual Mintek. So visual Mintek is the sort of a software that helps to solve all these problems in a very easy manner. So whatever equations, alpha naught and everything that I have given you, Visual Mintek already has all those equations, and just by putting some values, like for example, just by giving some CT values and the pH, it will give you all other values, alkalinity or H2CO3, whatever we wanted to calculate, right? Instead of writing those big equation, we can simply use Visual Mintek to solve the problems. So in this week, he has introduced this Visual Mintek. So there will be questions of Visual Mintek also. So it will be better if you have the software, then it will be easier for us to solve that. So all these equations, that mass balance, charge balance, equilibrium balance, and component balance, all these equations we have used to solve the problems, right? So all these things can be easily done in Visual Mintek. Okay, we don't have to write any mass balance equations. However, for some problems, we have to do some in-hand problems, in-hand solutions, like for the component balance and species, the tableau that we have prepared, like this species and all, na, that we may have to prepare for feeding in the Visual Mintek, because this Visual Mintek is very basic stage now. So that is why we have to do. So here these questions are simple questions. Okay, based on equations. So a monoprotic acid, my slides are not changing, right? Yeah. So a monoprotic acid HA dissociates in water as below. H plus, HA is being changing to H plus and A minus. Okay, we know the pKa value. The concentration of deprotonated form of A and A total at the equilibrium are 10 raised to power minus 4.8 and 10 raised to power minus 3.5 molar. What will be the pH of the solution? So very simple. So try to find out answer of this question. You can give the answer in the chat box. We have total 80 and we have A negative also, and we know this equation and we know the pKa value. So depending upon that, for most of the system, we'll be aware of pKa value, pKa1 or pKa2, we'll be aware of all these values. So what will be the solution for this question? I'll give you a couple of minutes to solve them. You can give your answer in the chat box. Next week, we'll study about this equilibrium diagram in detail. Okay, we'll see the solution now. So we have A negative as 10 raised to power deprotonated form of A as 10 raised to power minus 4.8. AT means total of A is 10 raised to power minus 3.5. Here the twist is, like earlier weeks we were directly given HA, right? But here we have given AT. So you have to use the component balance equation, like all those equations that has been taught. pKa we know, and this is the Henderson-Hasselbalch equation. So here we do not know HA, so that is important for measuring the pH, right? We know from the component balance AT is equal to HA plus A negative. So these are the species and these are the components that were required to form that. HA we can easily calculate just by putting it in the equation, we will get the pH. So while solving questions in the examination, also be very careful if AT is given or HA is given. Be very careful about that. Please note this down. Coming to the next question. Here we are talking about acetic acid. Similar kind of question is there. pKa we have been given. The pH of the resulting solution is 5. We know the resulting solution pH. The concentration of acetate ion, here negative will be here, at equilibrium is 10 raised to power minus 2.3. Calculate the total concentration of acetate. Here we want to know the total concentration of acetate, not acetic acid. So similar kind of question is there. Try to solve it by yourself. We'll see the solution in a while. Similar kind of question there. Instead of pH, here instead of total acetate ion, it is just like the question has been reversed. There we needed to find the pH, here we needed to find the total acetate ion. So use all this component balance concept and try to find out the answer. You can give the answer in the chat box. Even if you don't want to give the answer, keep the answer, like at least try to solve it with the class. Otherwise, at the end of the session, at the end of 12 week, there will be too many things to solve. So at least it will be better if you can hands on something. We'll see the solution. The solution is 10 raised to power minus 2.1 mole. Okay, we'll see how we are getting to it. So acetate, as I told, it is 10 raised to power minus 2.3 molar. pH is 5, pKa is given. Just putting in the equation from here, we can get HAC, right? Just by putting it in the component balance, we can simply get our acetate, total acetate. Because from Henderson-Hasselbalch equation, we can get only the proton donor at that time. We cannot get total. We can get only the proton donor, as I told, right? This will be proton acceptor divided by proton donor, right? So we can get only the proton donor by using Anderson-Hasselbalch equation. So this will be the total. Please check calculations also. Moving towards next question. Compute the pH of 5 into 10 raised to power minus 8 molar HCl solution. Ignore the effect of ionic strength and assume that AI is equal to Ci. Okay. Normally, if this thing is given is like less than something less than 7, if this raised to power is less than 7, okay, less than 7 means either 4, 3, we can simply write, right? Negative log of hydronium ion concentration. We can simply write. But when this is more than 7, means this is very weak acid solution. Even though it is strong acid, it is in so low in concentration that it is forming a weak acid solution. Okay, I have a question here, interesting question. Let's say I have a container of mm, 1 liter, and if I add here 500 ml of acid and 500 ml water, what will be the pH? Like if it will be less than 7 or more than 7? Obviously, it will be less than 7. But if I have another container of, let's say, 500 liter, and I add 1 spoon of acid, so it will be what? Acidic or neutral? And what can be the pH? Like, I'll rephrase it. I have a container of 1,000 liters. Like, let's say I have a big tank that we have in our homes, and I added just 1 spoon or 1 ml of acid, HCl, concentrated HCl. So, will the solution be acidic or basic or neutral? And what can be the pH? If the pH will be less than 7 or 7 or more than 7. So, you think about this question while solving this. Okay. So even if one drop of acid is there in a large volume of container, the solution will be acidic. Why? Because pH will be less than 7 in all the cases. It may be 6.99999999999, but it will never be 7, even if one drop of acid is there. Okay, you will not feel anything, nothing, but even if one drop of acid is there in large volume of sample, the pH will be never be 7 or more than 7. It will always be 6.9 and million times 9, but never 7. So that is a theoretical concept of calculating the pH. So in theory, it will never be 7, because whatever the solution be, even if one drop, there will be some H plus. And if there is some H plus, it will give some acidity, theoretically. And practically also, if you are using some pH probe, if it is not sensitive, it will give value 7. If it is costly and a bit sensitive, it for up to 6.99 it may give value. But if it is, even if it is most sensitive, it will give the 6.999. After that, it won't give the value. But theoretically, it is always possible to have pH less than 7, even if acid is added in a large volume of container. So keeping that in mind, we know here we cannot give the approximate solution to solve to get the pH, right? We need all those analysis. H plus H plus coming from this plus H plus coming from water. So we need to consider both for solving such kind of question. So here both the things will be dissociated, water and HCl. So try to solve this one. If we use approximate solution, the pH can be more than 8, right? 5 into 10 raised to power minus 8 hydrodynamic concentration. So pH will be more than 8 if we use approximate solution. But as I told, even if the acid is in very, very, very low concentration, pH can never be more than 7. It will be rather less. So pH will be less than 7 only, but you need to find out how. We'll see the solution. So pH is 6.89, as I told. It will never be 7. 6.89. We'll see how. HCl not means total HCl is 5 into 10 raised to power minus 8. So pK is less than 0, it will dissociate completely and blah blah, all those things. So these are the species and component that we got. So we'll prepare the W. These are the component and these are the species. Just putting all those things. Note this down, W thing, then we'll go further. Okay. Once you get this W, what is the formation equation? Like as I told earlier, right? What was acidity? If we talk about carbonic acid system, it was 2H2CO3 plus HCO3 negative plus H plus minus OH. This is what I told you earlier, right? But since here it is plain solution, it is not a natural solution. These two things are not there. But these things are there. So you can get it from W also, and you can get directly from the main equation. So what is total? What total is? For acidity, H plus minus OH. This is not CT. This will be for total of acidity. H plus minus OH. So that is what is written here in terms of W. Okay, all those things. From the above equation, this is the equation, and simply how we can write OH, right? OH will be ionic product of water by H plus. So this is what which have been written here. Simply putting all the values, we will get H plus. Once we get H plus, what is pH? Negative log of hydrogen ion concentration, and simply we can get the pH. So this question either W or simple basic equation that we have learned of acidity and alkalinity and everything. Okay, note this down. We'll move towards the next question. Okay, coming to next one. Cyanide ion is vital in metal plating industries because it can keep metal dissolved under condition where they would otherwise be solids or precipitate, and it may settle down. So cyanide is there to actually cyanide is used for complex formation. So you will study about its solubility in I think maybe 2 weeks later. So there we will study about the complex compound, complex formation, forming compounds. So we use those compounds to keep something in suspension, keep the other metal ion in suspension. So it is essential to maintain pH greater than 10.5 in these solution to minimize the release of toxic hydrogen cyanide gas. Okay, so HCN is there. Hydrogen cyanide may form if the pH goes beyond 10.5. So if the solution is prepared by dissolving 10 raised to minus 2 molar NaCN in water, select whether the below statement is true or false. The pH of the solution will be in the range to minimize the release of toxic gas. True or false? Try to solve this question. And how this is happening. You need to solve the whole question, then you will get if it is true or false. Means what you need to do is to find out the pH. Okay, if the pH is greater than 10.5, then there will be release of gases, and if it is less than 10, we need to keep the pH greater than 10.5. If it is less than 10.5, there will be release of gases, toxic hydrogen cyanide gas. To solve this question, you can use visual Mintek also. We'll see. So NaCN not is 10 raised to power minus 2 molar. So it is given. So there is no other source of Na or Cn in the solution. We can say Na total is equal to Na, which is coming from NaCN naught. So this you can write from tableau also. Here I have written, okay, NCN you can get from NaCN. You can write these equations like this. Okay, these are our component and these are the different species. So what we need to do is find out H total. Okay, so H total is what? I'll write clearly. H total is H plus HCN minus OH. Okay, and we can do like for this question there is no source of these, right? There is just water, and we need to find out the pH where HCN will be formed if the pH is greater than, if the pH is less than 10.5, right? Okay, so we can simply feed these values in Visual Mintek also, Na and Cn, and the resulting solution that we will get will be pH more than 10.5. Okay, it is little bit greater than 10.5, hence we will see that there is no HCN gases formed. We can simply solve this also. We want to calculate H total, and we have other solutions also, like we can solve it manually. CN total, how we can write? CN negative plus HCN, and we can write Na total as Na plus. Okay, for Na we will know. So how we can solve this? For Na we know that it is 10.2. So Na total we got. Okay, Na plus is equal to Na total. So Na plus is 10.2. One thing is solved. Coming to, we know that Cn total. Cn total is 10 raised to power minus 2. And from here, like HCN is breaking only, right? NaCN is breaking only, right? So the quantity of Na plus will be equal to the quantity of this. From here we get HCN, which is equal to 0. Okay, we will put this HCN here, which is equal to 0, and H total is equal to H plus minus OH. For this question, it is easier to solve, but if this question has many complexities like carbonic acid system, it will be very difficult to solve. Okay, so we need just to calculate H plus minus OH. So how should we go for this? We have Na and we have Cn. We need just to calculate the H plus. HCN is coming 0, H plus and OH. And OH is Kw minus H plus. Okay. Now HCN won't be 0. there should be some other value coming to HCN. Okay, I'll while uploading this session, I will solve one question based on this fact. Here we have used Visual Mintek, but I will use the tableau and solve this question, then we will get the answer. Okay, let's talk about next question. A solution is formed by mixing an equal amount of H2SO4 and Na2SO4 in water. Initial concentration of H2SO4 and Na2SO4 are 10 raised to power minus 3 and 10 raised to power minus 4 molar. Assume both compounds dissociate completely and can be neglected at equilibrium. Okay, these are completely dissociating. So find the pH of the resulting solution. Here also either you can use Visual Mintek or you can solve this problem using the basic W method, solving different equations, component balance and charge balance, whatever is required, as we discussed earlier in the maybe second week, like that you can use this. So if it is better to use Visual Mintek for faster solution, so try to solve this question. We'll see the solution in a while. So the answer that you can see here is 2.75. So how we got that? H2SO4 not is 10 raised to power minus 3 and Na2SO4 not is 10 raised to power minus 4. These are the species and these are the components. So we will be forming a tableau. So Na plus is, if you talk about Na, how it is forming? 1 Na plus and 2 of Na2SO4. Okay? Because here from here 2 Na will come now, so that is why we are keeping 2, which is equal to this not value, 2 into 10 raised to power minus 4. Talking about sulfate, similarly, 1 from here, 1 from here, and 1 from here. So that is why 1, 1, 1, and we will get these value. And HT is minus 1 from OH and 2 from here, and 1 is H plus. So very simple. We have NaTSO4, all these values we have. Okay, so we can solve this also, but it will be easier to solve it using Visual Mintek. So we can keep all these values in Visual Mintek like this. There will be the, we have to fit all the components in the present problem. There will be a column to keep all the components. That is why even if you want to solve it in Visual Mintek, you need to prepare the tableau and all. So we'll just be keeping all these things. Here it is already in millimolar concentration. So that is why we are neglecting all these minus 3 values. And here we are putting it as 0.2 into 10 raised to power minus 3. So that is all we are putting here. And when we will click here on species table, we will get all the results. So we will get H plus, HSO4 and all other things which are available at that particular point will be given, and from here we can just get the pH 2.756. So these questions can be made very simpler just by using the visual Mintek. So a very direct question is there. Coming to next question. Significant inhabitants of cities suddenly suffer from waterborne disease. As being an environmental engineer, you are advised to check various parameters of potable water supplied across the city. Parameters include both chemical and biological. After assessing the effluent of the water treatment plant, you found out a class of bacteria. There is a class of bacteria present in water causing the outbreak in the city. Luckily, after laboratory testing, it was noticed that bacteria only survive in alkaline water. Okay, so if the water is alkaline, so the bacteria is surviving. What we want to do, we want to reduce the pH to make the water little bit acidic. So to control pH, what is happening? 6 into 10 raised to power minus 4 molar HPR is added, which reduce the pH of water to this. Okay, but we are reducing the pH to this, but we cannot drink this pH water. What we can drink is, for the potable water, it should be 6.5 to 8.5. If it is beyond this range, we should not drink that water. It won't be good for our to maintain the salt concentration in our body. So this is the range of drinkable drinking water. Okay, as per IS 102, I think I'm forgetting 10200. I guess, or I'll confirm it. As per IS code, this is the range of water that we should drink, and this is based on designated best use of water also. So, it when the pH reached this, it destroyed the significant population of bacteria. To neutralize the water for domestic use, 3 into 10 raised to power minus 4 molar NaOH is added. So the pH increased slightly. Why pH is increasing slightly even if we are adding NaOH? Because this is forming a buffer. Okay, so there is only slight increase in pH, not a sudden drop, not a sudden rise. So for decreasing more H plus, again this much is added. So it seems like when this was added, it reached to a buffer zone of NaPr. Then more H plus was added, then it was increasing drastically. Okay, so what will be the pH of water? So multiple step problem is there. So first it is added, it reached a buffer zone, and then it is added again to increase the pH of water in the drinkable range. So what is the pH of water if we want to make it into a drinkable range? Visual Mintek can be used after preparing the tableau and all. Try to solve this one. Okay. So the answer is 5.11 in this case. Even though the pH is 5.11, it is not in the drinkable range. So for this question, it's okay to get 5.11, but we'll need to add more NaOH to increase the pH. We need to add, okay. So what we are doing? Firstly, we are adding 6 into 10 raised to power minus 4 HPR. Then we are adding 3 into 10 raised to power minus 4 NaOH. Then we are adding 2 into 10 raised to power minus 4 NaPr. Okay. H total will be given by HPR and NaOH because H plus is what? H plus given by HPR minus OH, no? So OH, this is the OH that we subtract. We got H total. Propanoic, propanoic acid, HPR, NaPr. Okay, we will get this. And total sodium, how from where we are getting? Sodium propanoate and NaOH. So we need to calculate all these total. You can use the tableau to prepare this, and these values we will feed in Visual Mintet simply. Just we need to put all these values here and click on species tableau and we will get the result. Okay, again all these values are in millimole. So that is why we are omitting this 10 raised to power minus 4 thing and we are making it into 10 raised to power minus 3 terms. So that is why this will become 0.3 into 10 raised to power minus 3. And that is what we are feeding here. Propionate will become 0.8 into 10 raised to power minus 3 and sodium will become 0.5 into 10 raised to power minus 3. So that is what we are feeding here in millimolar concentration. And this is what we got. And pH is 5.104. pH is 5.104, but still it is not in the drinkable range. Okay. As I told you, it should be 6.5. So this is not a practical problem. This was just a hypothetical problem, and whatever they have added is in hypothetical case. So as an environmental engineer, we should target the pH. Okay, pH I want to increase to 7. Then how much should I add? We should have targeted it like this. Okay, so this is just for the example problem, but not the correct thing that we have done. Coming to next example, hydrochloric acid is a weak acid that is used extensively in industry because fluoride ion attaches firmly to iron and aluminum ion. As a result, it is an excellent reagent for removing surface scales from the object made of iron and aluminum before they are painted or other surface finishing operations are carried out. Compute the pH of the solution prepared by adding 10 raised to power minus 3 molar HF. You know the pK value, we know the total H. So we are adding this much HF in pure water. What will be the value? If it would have been strong acid, then we can simply write pH as 3. But since it is weak acid, the water will also dissociate. So HT will be H plus coming from water, HF minus OH. So HT just getting equal to H plus will not be there. There will be HF also, undissociated HF and OH also. So what will we need to find out this HT in order to find out the pH. Can we use Henderson-Hasselbalch equation? For this also we need, if even if we use Anderson-Hasselbalch equation from here, we can calculate F, right? We cannot calculate. Either we need F to apply Henderson-Hasselbalch equation also. Either we need F or we need pH. What will be the F total? It will be F plus HF. The answer is 3.26. Okay. As I told, HT is equal to HF, H plus HF. Okay, there will be minus OH also, but since it is saying it is added in pure water, no OH is coming into picture, but there should be ideally minus OH. Ft is equal to F plus HF. So HF is equal to, now we are using ionization fraction thing, alpha naught Ft. So alpha naught, how we will write alpha naught? H plus upon Ka plus H plus. Just by putting all these values in here, we can just by putting all these values in this equation and solving for H, we will get H plus this much, and then pH will be 3.26. Even if we put minus OH here, the answer will only slightly change. Instead of 3.26, there will be like 3.3 or something. So you can put minus OH here also. In this question, in this solution, it is not there. This minus OH will become Kw upon H plus, which can be solved here, right? It can be kept here and solved, and we will simply get the value of H plus. So it's better to keep minus OH to avoid the confusion. Moving towards next one. A solution is made by adding 10 raised to power minus 3 molar hypochlorite and 10 raised to power minus 3 molar sodium propionate to water. When sodium propionate is dissolved, sodium ions are released and undergo no further reaction. Then NaOH is added until the solution pH is 7. How much NaOH must be added? Okay, we have the target pH. So this is reverse problem, reverse pH problem. So we have the target pH. How much? So this will be solved by trial and error. How much NaOH should be added to make the pH 12? So what all things are there? 10 raised to power minus 3 HOCl, then 10 raised to power minus 3 NaPr, then some X amount of NaOH. pH is 7. So H plus is what? 10 raised to power minus 7. We have Ka of HOCl, Ka of HBr. All these things we have. How do we go for this question? We'll see. So answer is 2.22 into 10 raised to power minus 4. So this is the solution. HCl naught is 10 raised to power minus 3, NaPr is 10 raised to power minus 3. pH is 7. So these are different species and component. Coming to relevant equation, we can form different relevant equation for that, right? So equilibrium relation, Kw is equal to 10 raised to power minus 14, KPr is given and KHCl is also given. These things are given. So please note this down and then I'll show you next slide to start the question. Please note these values down. At least these things you should note down. And species and component. So now putting the mass balance equation of propanedione total, OCl total, and we need to calculate Na total in order to get NaOH, right? And we are putting charge balance also because in this question, up till all the problems that we have solved till now, charge balance was not involved, but here we have to involve. And I have written the result. In this problem, NaT plus is unknown since we do not know how much NaOH has been added to adjust the pH to 7. Therefore, we have three equilibrium expressions, two mass balance and a charge balance to work with. Six independent equations. Here there were six unknowns, right? Okay, if we know H plus, we can know OH minus. So here we can say 7 minus 1, 6 unknowns. So to solve that, we need 6 equations. So those 6 equations are there, and the one equation is coming from the charge balance. So there are 7 species in the system, but one of them for which the final concentration is specified. Thus, the number of equation matches the number of unknowns, and the problem can be solved. Now substituting in the charge balance equation, we are putting all the values in the charge balance equation, calculating the ionization fraction and substituting all the values in the charge balance, we will get the result. Please note this down. It is very straightforward. Note this down. So coming to question number 9, what will be the pH of 100 ml of 1 into 10 raised to power minus 3 molar solution of sodium hypochlorite to which 25, this is mixing problem, 25 ml of 2 into 10 raised to power minus 3 molar HCl is added. 100 ml 10 raised to power minus 3 molar hypochlorite is there in this 25 ml 2 into 10 raised to power minus 3 molar HCl is added. So what will be the pH? Answer is 7.52. We know that NaOCl is given, HCl is given. So total H will be from NaOCl will be 0 because no H is there in NaOCl, right? So OCl total from NaOCl will be 1 into 10 raised to power minus 3. Huh? Na will be 1 into 10 raised to power minus 3 and Cl from this will be 0. Similarly, for hydrogen total from HCl, OCl and all those things will put it. These are all conservative quantities, hence we will simply find out the mix problem. These are conservative quantities, it means they are not going to change with time. There will be no degradation or complex formation in these quantities. So we can simply find out the mix. We can simply determine all these HT, OCLT or NAT values. And we can put them directly in Visual Mintech and solve the problem. Just put these values all in Visual Mintech and you will get the result. And you will get the pH. Coming to the last question, you have a flask in a laboratory on which the label is smudged. Okay, from what you can read, it is solution of monoprotic acid, we call it HF, at the concentration of 2 into 10 raised to power minus 3 molar in a 0.05 molar NaCl solution. You measure the pH of the solution and get the reading of 3.09. Determine the pKa of the acid. How we can determine the pKa of the acid? We'll jump to the solution. pH is given and H plus we know from the pH. HT is 2 into 10 raised to power minus 3 molar because it was given the HX concentration is that. So XT also we know. NAT we know and CLT also we know because it was kept in NaCl solution. Alpha naught is HX upon XT. HT we know HX plus H plus minus OH. In that problem they omitted OH but here they have taken it and you do no need to omit it. You can simply put Kw by H plus and we will get Hx value as this. Just putting it in alpha naught, we get the alpha naught. And alpha naught, the other form of alpha naught is H plus upon H plus plus K. We got K and we can calculate pKa value. So note this down. pKa is 3.25. So this was the last question for the session. So thank you for attending. I'll close the session now. You can note this down. I'll close the session. Thank you.